Assalamu alaikum. Honorable Keynote Speaker, Session Chair, respected colleagues, and dear students, welcome to our first session of series webinar organized by the Department of Tripoli, Green University of Bangladesh. Our today's session will highlight the importance of Matlab, a promising programming language of today's world in advanced Tripoli study. We are fortunate to have Dr. Ahsanul Alam sir, Associate Professor, Department of Tripoli, Green University of Bangladesh, as our today's keynote speaker. We also have Dr. ASM Shihavuddin, Honorable Chairperson, Department of Tripoli, as a session chair of today's webinar. We will have a question answer session at the end of the webinar, and you can ask during that session. Now, I would like to request Dr. ASM Shihavuddin sir to say something about our webinar series. Dr. ASM Shihavuddin, Chairperson, Department of Tripoli, Green University of Bangladesh.
Thank you very much, Shajan Madam, and welcome everyone to our session today. We're very happy to have this session right after our midterm, so that we feel relaxed and we enjoy the session with our Dr. Ahsanul Alam sir. He has a very wide experience in teaching plus engineering technical knowledge, and he would like to share with us some of the things that we need to know about Matlab. And in my experience, when I was a graduate student, I used to be very afraid of using Matlab because I knew few commands, and whenever there was a problem that I would like to solve on my own, I felt really nervous. But during my masters, I thought like I have to get over this fear of using this tool because it's very important. And I started solving problems on my own, and it took a much more longer time than my colleagues, but it helped me really to get the confidence in Matlab. So I hope Ahsanul Alam sir will show us some methods how to approach the problem, and I would request all our faculty members, our students, that you take the inspiration from here and you try on your own to solve some problems using Matlab, and then you get the right confidence to really grow and use this tool for your research or any other engineering problem solving. So, and thank you very much for hosting this session and also the organizing team. And looking forward to the session. Thank you.
Thank you, sir, for your motivational speech. So now I would like to request our keynote speaker, Dr. Ahsanul Alam sir, to start his session. Dr. Ahsanul Alam, Associate Professor, Department of Tripoli, Green University of Bangladesh.
Bismillahirrahmanirrahim, and very good afternoon. And thank you, Madam Jahan Madam, and our chairman for nice introduction. In today's webinar, I welcome everybody. So my name is Ahsanul Alam, as you know, and already introduced, and I am in the Tripoli department. So for today's presentation, actually, 1 minute. The objective of today's presentation or today's webinar is to demonstrate how Matlab can be used as an integral part of learning process, and how a student can go beyond the classroom learning, and how they can have deeper understanding of a topic, especially electrical courses. So in my today's presentation, there is a brief introduction and background of the Matlab, and I will go for solving linear system, and solving nonlinear system, solving dynamic systems, and characterizing renewable energy sources. So if you look at the background of the Matlab, excuse me, I am audible to everybody?
Yes, sir.
Yes, sir.
And the screen is visible to everybody?
Yes, sir.
Yes,
It's
sir.
visible.
Okay, very good. So the Matlab stands for Matrix Laboratory. In fact, some of us pronounce it in a wrong way. Somebody says Matlab. This is not actually Matlab, it is Matlab. This MAT stands for matrix, and lab stands for the laboratory. And it was actually originally conceived in University of New Mexico by Philip Monar in 1970. And within very short time, it received very high popularity among the academia and industry. Nowadays, yesterday I was checking the Matlab website, more than 6,500 universities are using the Matlab. And in the industry also, so altogether around there is almost 2 million users. So the beauty of the Matlab is it has strength in performing mathematical computation and signal processing, analyzing and visualizing data. It has, in fact, excellent graphics tools. Also, it helps modeling physical system and phenomena. And also, it can go for testing engineering designs. So for more information, you can go to this website in this link. And even in the MathWorks, if you give the Google search, it will immediately give you the website for the Matlab. So I'll not go further the history of the Matlab. So if you, the Matlab is, it's progressing all the time. And it has a very strong team for the development, and it reached in such a developed state that it can take your idea to realization level, all the way modeling, design, simulation, prototyping, testing, validation, all the things you can do with Matlab. And it is actually creating the wide spread of area and avenue for almost everybody. So the utilities and power engineers, they can use it. The robotics people, they can use it. The communication people, they can use it. And aircraft and defense, automotive, also the electronics, industrial automation and machineries, and even the biotech, pharmaceuticals and medical and computer security, finance, and many more. As I said, it is creating the avenue for almost everybody gradually. So this is the brief history and background of Matlab. So now in this presentation, I will assume that everybody has at least little background on Matlab, because in our previous session, we already conducted Matlab for the beginners, Matlab for the engineers. So I will go a little bit beyond further to that. I will not start from the bottom level. So if you look at the Matlab windows and desktop, it has the command window, the workspace window, the current folder window, and command history window. So this is the command window, and you can rearrange this through this layout. So this is the current folder window. This is the workspace, and there is also history. So if you can retrieve this history when you need for certain command. Let's say you use it before, and you want to use it now again, so you can retrieve it. And for the operators and operation, I will not go for details of everything. I will review the frequently used operators. So most commonly used operator we use, this is the we call it the colon operator. So it has the starting, and it has the increment, and it has the end value. So let's say x equal to, if we dial it 0 to 8, then it will start from 0. It will create, in fact, an array that will start from 0, increment by 2, and reach 8. If the last increment is greater than this, then it will take the value before this. So hopefully you know this basic. And another is the array indexing. So that is also very useful. So let's say we create two arrays. One is U and another is W. And this W is 5 times sin U. So from there we can, let's say we want to see the 7th element. So if we write this, then it will give you the 7th element. If for the W, if you write like this, then it will give you the 7th element of the W array. And for the operation, we frequently use this dot operation. That is called the element by element multiplication. So if we have two arrays, x1 and x and y, so this dot product will give you multiplication of x1 times y1, x2 times what. It will create another array, and that array will be like this. So examples are like this. I hope you have this background. So I will not go on further of this. And we frequently also use this kind of other, even for the matrix also, we can have this kind of array multiplication, sorry, dot multiplication. So that will give you this element by element multiplication and the division also. So basically today I will go for more on examples. And for writing program, as we know, we frequently use CLC for clearing screen and clearing the variables. And even we can clear certain variables also by giving a specific name, like clear variable 1 or 2, something like this. And with the exist, we can check whether this variable exists in this workspace or not, like this. So now let us look at very simple program, because I will start with a very simple one, and with the command window calculation. So let's say we are clearing our screen and clearing the variable space also. And then we are creating a X array starting from 0 to 70 with increment of this. And we want to create another array that is Y1, that is like this. And we want to plot and see the graph of Y1 versus the X1, or X1 versus Y1. So this will simply, it will look like this. We know that this is simply a cosine function. So it will look like this. So if we create another one, and the same array, but a different equation, and plot it, so it will simply like this. This is the exponential decaying function. And we can merge two plots together. Like this, if we want to plot the previous one and this one together, then we can use this kind of command, plot command, and very simple command for plotting. And it will give you the two graphs together. So now let's say we want to create another graph that is multiplication of this sinusoidal function and an exponential function. Here we are using this dot product, or element by element multiplication. So what it will generate? It will generate this is called the damped sinusoid wave. So in fact, this is damping the amplitude of this cosine wave. So the ultimate waveform will look like this. Now let us go for our courses. In our electrical circuit course, we use this nodal equation or loop equations to find the node voltage or loop current or other unknowns. So it will be very handy and very simple to solve large circuit with a large number of nodes. Just by writing this node equations and then rearranging this in a matrix form. Let's say we have 3 nodes, VA, VB, and VC. So with a single command, you can get the node voltages. So for this is my A matrix, which is this one, and this is the B matrix, which is in the right side, and with the single command, either A inverse B, we can write it, or this A \B, that will give you, in fact, this operation and give you this result. So this is one step solution. So I will not go for this one in the Matlab running program. I will go for a little bit complex programs. So for the large or complex programs, we'll go for the script file, or we frequently call it the M file. So this M file is the collection of executable commands. So just now I showed you this command window, some command. We can put it all the commands or all the plot commands in certain window or editor window, and then we can run it together. So that file is called the script file, and it is very useful for executing the lot of Matlab commands. And we have also some pre-built command in Matlab like plot, mean, standard deviation, exponential, cosine D, like this. These are the built-in. We can also create our user-defined or customized M file by writing our own program or own function also. So for this, what we do, we go for this new script file, then it will create a window like this, and here we can type our this program. And for the loop control statement, actually we use several either if statement or the loop or while loop. So frequently we use these two loops. One is called the for loops, and another is called the while loops. So for the for loop, actually it will this array will decide how many loop it will continue. The number of the element in this array will decide. That is, it will start with the first element and then continue and reach to the last element, then come out from the loop. So this is how the for loop works. But for the while loop, we give here a condition. So this condition will decide whether it will continue or not. So as long as this condition is true, then it will continue this loop. If it is false, then it will come out from the loop. So there must be an expression inside the loop that will update this condition, so that that is update this variable x, so that at some time it will come out from the loop. So this is the things as I explained. Now look for another example. Let's say we have a in fact it is a band pass filter, and we want to see its characteristics. So and the requirement is plot this is called the transfer function versus the frequency, and find the resonance frequency and find the bandwidth. So for this, what will we do? We have this, and this is called the your transfer function. So we will just solve this equation for different frequencies, and after that we plot it. Only 3 steps. So that is the things I am doing here. I am creating an array for different frequencies and then solving that equation for different frequencies, and after that I am plotting it. This is as simple as this. And now this we can solve this even without a for loop. And how we can do it? We will just create another array of the numerator and another one denominator, and then do this that is element by element operation or the division. Then that will give you the same value as with the for loop. So sometimes this element by element or the dot operation will make our programming very simple, very easy to understand. and that will give you the same kind of plot. Now, what is after this plotting? We want to find the bandwidth and the resonance frequency. So the resonance frequency is the peak, the value at where the peak is. So we can, or we call it the center frequency. So from the graph, we can find it easily. And also for the bandwidth. So for the bandwidth, we find two cutoff frequencies. One is called the F1, another is called the F2. So how we'll decide this cutoff frequency? So this is called the half power point or the level. So where the power will be half of this resonance frequency. So we can draw a line, this one, using this simple command. This command will be simply like this for the half power point, and then we can plot that command also. This is a horizontal line, and from there we can find the intersection of these two frequencies, and that will give you the bandwidth. So in this way, we can solve our this AC circuits problems or visualize its characteristics. And this is how we are doing the processing. And let's say we want to see the band stop filter characteristics. So this is a circuit for the band stop. And again, if we want to find the similar things, then we can again solve this characteristics equation and plot it, and then we can see the variation of its transfer function with the frequency. So this is definitely, this is my center frequency, where the value of this will be the minimum. For the band stop, it will be minimum. For the band pass, it will be the maximum. And we can also find its the center, cutoff frequencies by drawing this half power line. Now let us go for the signal and system course. For the signal and system course, frequently we use the Fourier series. And let's say for a square wave, this is the Fourier series for a square wave. Now, let's say we want to see reconstruction of the signal back to our square wave. So this series is basically nothing but the summation of sinusoidal waves of various frequencies. So the first one, we call it this fundamental frequency signal, and the others is we call it the harmonics. So what will we do? So if we run this for the fundamental frequency only, then we can see this kind of very sinusoidal waveform. But as we keep on increasing the number of harmonics, it will slowly turn to the square wave. I will show you this thing so that a square wave, let's say for the square wave, this run button is here. So this is for the fundamental frequency. So as we keep on increasing the harmonics, that is adding the harmonics, it is slowly turning to our the square wave shape, or it is reconstructing. In fact, it is reconstructing. And here I'm considering only 51 odd harmonics. So that means adding all the harmonics up to the 51. It is giving us this kind of reconstruction. And for the other one, let's say, Okay, for this, we are just executing this simple equation with this for loops. Very simple. Here is data, all our data. And here is the plotting. So the main calculation here, very simple. And this calculation is starting with the fundamental one, fundamental frequency signal, and then keep on adding the other harmonics. And let's say another. This is called the triangular signal. And for this, the Fourier series is this. So now we can do the same operation, whatever we did for our square wave. So we need to solve this one in a for loop and then plot it. So if we go for this, you can see for a triangular wave, triangular wave. So if we run it, so this is for the fundamental wave. So if we keep on increasing the harmonics, so it is turning to our original triangular wave or reconstructing it. So it is almost the triangular wave. And further to this, what we are doing, we are plotting here the frequency spectrum or the harmonic spectrum. So here is the amplitude of the first harmonics, then second, then keep on this one. So from this information, what we can see that the first three, or that means the second and third harmonics, the first, second, and third harmonics, this is our dominant harmonics. After that, this is not dominant. So if we have only 3 or 4 harmonics, then we can get the reconstruction of our original signal.
স্যার একটু ইন্টারাপ্ট করি স্যার, আমরা মোস্ট অফ আপনার ওই শুধুমাত্র স্লাইডটাই দেখতে পাচ্ছি, অন্য কোনো স্ক্রিন দেখতে পাচ্ছিলাম না।
আচ্ছা 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 আচ্ছা,
আপনি যদি ওর আবার
স্লাইডের উপরে একটা ব্ল্যাক বক্স দেখা যাচ্ছে শুধু।
আচ্ছা 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 1 মিনিট, তাহলে আমাকে
আপনি স্ক্রিনটা অফ করে স্ক্রিন শেয়ারটা দেন স্যার।
যাচ্ছে না
স্যার? এখনো স্যার পাওয়ার পয়েন্ট স্লাইড দেখা যাচ্ছে স্যার। হ্যাঁ স্যার, এখন দেখা যাচ্ছে ম্যাথল্যাব।
এখন
আচ্ছা আচ্ছা, okay, so coming back to our discussion, let's say, so I will again go back to this band pass filter and then run it. So this is the waveform for our band pass filter. In fact, okay, so can you see the output of this?
Yes sir.
Okay.
Yes sir, yes sir.
Okay, okay, good. And for the band reject, so this is the output for the band reject filter. And the programs, as I showed you, the same coding we are using, or the similar coding we are using inside the Matlab also. So I will not spend time for that. Now I will go for this square wave Fourier series. So if we run this part, let me close this one. So for the fundamental frequency signal, we can see it. This is a nice sinusoidal waveform. So as we keep on increasing the harmonics, so or adding the harmonics, so it will turn to slowly this square wave, or it is basically reconstructing the square wave. Reconstructing. So can you see it?
Yes,
everybody?
Yes,
Okay. Okay. Now for the triangular wave, the similar things. what you missed out, just quickly. It's taking time. I don't know why it is taking time. Okay. I don't know why it is taking time. I don't know. It is running in the background. Okay. Okay. I did not finish actually that one. That's why it did not finish. Okay, for the triangular, we are doing the similar thing. So this is for the fundamental wave. So if we keep on adding the harmonics, then it will slowly turn to original triangular wave. And as I said, we want to see its the spectrum plot also. Spectrum plot. So that one. Actually, it ran. So this is the spectrum plot. So from this, we can see the fundamental harmonics, or the fundamental waveform, it has the highest influence. And the second harmonics, this is a little bit. And the third one, after that, these harmonics are insignificant. So its contribution to the reconstruction of the original signal, this is insignificant. So basically here we need these three components to reconstruct the signal. Okay, now I will go further. Okay, for the, can you see the screen now? I just now.
Yes, sir.
PowerPoint. Okay.
Yes, sir.
Now for the solution of this nonlinear equations. So let's say we have this as a nonlinear equation, and I'm starting with a very simple one. And then we will slowly move to the complicated one. So we have to solve it using Newton-Raphson method. And in fact, for solving this nonlinear equations, we need the iterative method for solving it. And we have a lot of iterative algorithms, this Newton-Raphson, Gauss-Seidel, and many others. So Newton-Raphson, this is a very popular one. So for this, we have to find the differentiation of the function, and we have to evaluate the two things. One is the function itself, and the differentiation of it. So we will start with the initial value. 0 stands for the initial value. So we are evaluating at the initial value this function itself and the its derivative, and then finding the increment and then updating this variable or the unknown. So we will keep on this thing in a for loop or in a while loop until we satisfy our the requirement, or we reach the accuracy. So that is the things we are doing here in a while loop. So we are solving this three things. This DC, we will say delta C, sorry. Delta C, and then this is the Jacobian, that means the derivative of this function. And then we are calculating the delta X, then updating it. So this is the thing we are doing. So if we look at the output, if we run it, we will see that after 5 iteration, this increment became 0, or the change of the variable become 0. So this one is my solution. And we can see this thing in our Matlab. Just tell me if you do not see this Matlab window. Can you see the result? Hello?
Yes, sir.
Yes, sir.
Okay, so here this is the result. So this is very simple nonlinear equation, but in our real life, we go for the quite complicated one. And that is, right now I showed you that one is the first order or one-dimensional, we call it nonlinear equation. So if we go for the little bit higher level, that means this is called the two-dimensional. Here we have the two variables, x1 and x2, both are nonlinear. So the plot of these two function is like this. So from there, we have to solve this x1 and x2. Solve these two nonlinear equations using this iterative method. So since we have two unknown or the two variables, so we must have two initial value. So I start with this initial value. We will do the same procedure. That means we will evaluate this function itself at this initial value, then its derivative. Since we have two variables now, we have to have the partial derivative. So this partial derivative will have that is 4 derivatives altogether, and we will have a matrix of this that is called the Jacobian matrix. So we will evaluate this one, J and this function f1 and f2. So if we write a similar program, then run it, then we will see. Okay, I will show the output of this in the Matlab window for the second order. So here we can see the Jacobian matrix is become now 2 by 2. This delta x also 2. That means since we have two variables, so it will go everything in pair, x1 and x2. And finally, when the delta x become either 0 or close to 0, then that one is my solution. This is my solution. So in this way, we can go for higher order, even the 10th order or the 15th order or whatever order we like. The procedure will be the similar to this the second order system or second dimensional system. So now we will go for the function subprograms. That means right now we have used this plot or the standard deviation, whatever the function we are using now, that is the built-in. We can also create our own function. That is the user-defined function. And for this, as we have seen before, that Matlab which has the three command window, that is 3 windows. One is called the command window, another where we can write the script file, and another is we can create a function subprogram. So why we need this function subprogram? So that will also make our life very easy, because sometimes we have to use the certain routine or certain loop or certain program again and again. So in that case, instead of writing this thing everywhere, we can write a function subprogram and call it where we need it. And also it will make the understanding or the writing of the program very easier. So for this, there are 2 types of function subprogram. One is called the value returning program. That means it will return some value after running this program, subprogram. It will return. That means it will take some input, and then do the processing and return some value. Another is called the void functions. That means it will not return any value. We will see the example for both of these. So for creating this functions of programs, so we will again click this one, the new, and then the function, and then it will give us this kind of window. And here this output, this is the output variables, what the program will return, and this is the input variables. So we'll see this. So this function, it has the header. This is called the function. Oh, sorry, this with this color it will come. This is the output variable names. Here we'll put here, and this is the function name. And then this is the input. Whatever the inputs variables we are using. So we'll see some examples. Then it will be clear to us. So. When should we use this function? As I said, when we use a certain set of code in multiple places and or multiple programs even. Then, and what should we think before we create a function subprogram? That means what will be its input and what will be its output, and how this input and output will relate. So it will take this input as in the program, and it will produce the output, and here it will do the processing for the output. So we will look at some examples. So let's say this is for actually electrical power engineering course examples. Here we have the synchronous machine, and this synchronous machine is running as a motor. And this is also sometimes we do experiment in the lab. This is called the V-curve characteristics of a synchronous motor. That means for a constant power, that if we're running the machine at a constant power and change the field. So this synchronous machine, it has a section or field circuit. So if we change the input of the field current and then observe the variation of IA, then this variation of IA with the field current, it will take the shape of V. So that's why its name is V-curve. So how we can, okay, this is the vector diagram. And for a constant power, this vector diagram for IA and EA, it will be like this. So if we keep on changing IF, then EA will change. This is internal voltage. It is directly related to the IF. IF is producing flux, and this EA is directly related to this flux. So if we increase the IF, so my EA will increase. So with this increase, our IA will change in this fashion. That means the vertical component of the IA will remain fixed, and horizontal component of EA will remain fixed. So I will not go for the explaining of all these equations. So this is the theoretical waveform or the variation. And this is the lowest power or no load. This is for the half load, and this is for the full load. So now let us look at this thing in our Matlab. So this V-curve. Okay, so here I am doing it in two ways. One is this. Okay, so here is the program. So what we are, okay, let me run it. So this is for the no load. And if we keep on increasing, or that means run it for the higher load, then it every time this variation will look like same, only it will be shifted up. So this is for another load, this is for the another load, and this is for the another load. So here it is giving some information. So that means related to the power factor. So this lowest point, this is called the unity power factor point, unity power factor point. So if we add all this lowest point, then we can get a locus for the unity power factor. And right side of this is called the leading power factor region, and the left side, this is called the lagging power factor. So now the conclusion is by varying IF. So here is in this axis we have IF. 1 minute. So in this axis we have x-axis we have IF, and this is the IA. So now what we can see that by varying IF we can change the power factor of this machine. So this lagging power factor machine operation means the machine is drawing the reactive power, and the leading power factor means it is delivering this reactive power to the system. So this machine is very useful, or frequently we use it for power factor correction of a system, of our power system. And this is very popular use for the power system, that we can make a smooth variation of the power factor in the system. So this is the V curves, and this is the problem actually or the data I took from. And for calculation, I did only this 3 operation. From the power, I calculated the current, that is armature current, then EA and IF. Only by 3 these calculations, I can produce the graph. And for the that program was for a single power. So now if I vary this power, let's say start from 5 megawatt to 45 megawatt with the increment of 10, and then we have to do the same operation for in a for loop, or here I am using the element by element multiplication or the dot multiplication. So instead of using the for loop, I am avoiding this for loop by using this dot multiplication. And we have seen already the plot of this. Now, how we can do the same plot using the function subprogram. So here, this part we are calculating again and again and plotting for different power. So if we put it in a function subprogram and then call it in a main program, then our main program will look like very simple. So we are varying power and calling this subprograms and generating a plot, and then doing the same thing until the loop completes. So here, this program or this function subprogram, this is called the void one. That means it is not returning any value, just returning or giving me a curve only. So it does not have any output here. Only it is taking the input, this power, and it is doing the processing and generating a curve, V curve, and then again going for the another operation. Now we will go for another machine. This is called the induction machine. So how we can characterize this induction machine? So for this is the very simple equivalent circuit of an induction machine, and from there the Thevenin equivalent we can write it like this. So I will not go for the theory of this. And this is the torque developed equation inside the induction machine, electrical torque developed. So for generating this torque, we call it torque slip curve of the three-phase induction. We will solve this one. So for solving this one, we need this I2 and V Thevenin also. So basically we will solving this three equations. There's three equations. So let us solve it. And if we solve it, then we will get this kind of curve. And let us do it. So this is the output, but before we go for the output, let us solve this one in a Matlab. Curve and induction machine dot slip. Okay, so inside this my program, I am just solving only these three equations inside this for loop and generating this curve. So if we run it, okay. So this one, this is the characteristics curve for a single phase, sorry, three-phase induction motor, and this is called the torque slip characteristics. And this one we produce it for a certain value of R2. But if we keep on, I'm trying to pull it down. Anyway, if we keep on changing the R2, so what will be the effect of R2 on the torque slip characteristics? This is a very important information. That means this is very important observation also. So if we increase R2, then the curve shape will be similar to the previous one. If we keep on increasing, then it will take this kind of shape. If we keep on increasing this, then it will take this shape. So now, what information actually we are getting from here? That this maximum, okay, one. So this is the torque, and this is the speed. And we can see this maximum torque is remaining same. And it is not changing with the change of rotor resistance. But what it is changing the starting torque. This is called the starting torque. That means torque at zero speed, torque at zero speed, torque at zero speed, torque at zero speed. So with the lower value of R2, our starting torque requirement for the starting torque will be small. And if we increase it, then it will be higher, and then it will be higher and higher. So what this information will say to us, that if we need to run a loaded machine, then we need to increase it rotor resistance also, so that it will produce a higher starting torque. But at the end, we have to cut off this rotor resistance, because if we keep this rotor resistance a long time, higher rotor resistance, then we will have a higher loss. So at the beginning, for the starting purpose, we will increase the rotor resistance, then slowly it will cut down. So this is the information it is giving us. Now we will go for the dynamic equation solving or dynamic system. And in fact, more interesting result, or the we can say the analysis, we will see through the solution of dynamic system. So for solving dynamic system, we write this dynamic equations or the differential equations, and then we use the solver. So depending on the solution type or the equation type, we have different kind of solver. So this solver, it has mainly three parts. One is we have to write a function subprogram containing this differential equation. Then the time span, so for how long we want to see this analysis, and the initial value. So for solving any differential equation, you know we need the initial value. So if the differential equation is third order, we have to put three different initial values. And also we can have some other options also. So here is the description of all this. So whatever the order of the differential equation is, we have to write it in a set of first order differential equation. And then there are different kind of solver, 40, 23, 45, all this thing. So depending on the requirement, we will use or we will select our solver. So OD45, we frequently will use this one. So this is the selection criteria for different solver. So if it is a very stiff function, then we have to go for this 15S. If it is a non-stiff, then we can go for the 45 or this 123. And this is the just the selection criteria for the solver. So now let us look at the dynamic characteristics of our separately excited DC motor. So here you can see some interesting things. So let's say we have a DC motor and separately excited. That means field circuit is separate from the armature circuit. And if we suddenly turn on the machine by connecting, that is switching on with the full voltage, then what will happen? So that is the thing we want to see. So for this, we need to write the dynamic equation. So the dynamic equation is given by this. One is for the armature current and another for the speed. So this Vt, this is constant, Km constant. Here only the variable is Ia and omega m. The other things are constant. This is the inertia, this is the inductance, this is the load torque. So now we need to solve this thing using this ODE. And for this, we have to write a function subprogram. And this function subprogram will be this one. One is for the first equation, another is for the second one. Very simple, very simple. This is the second order. So here we are giving the name for the function subprogram. Here, this is the output it will return, and this is the input. So let's say we are calling this in a main program. So in the main program, we are just calling this function subprogram, and we are using this ODU45, and this is the time span, and this is the initial condition. So now, after running this, if we plot it, and remember here we are using the another plot command. This is the subplot. That means we want to see two plots in one page, and this is the coordinate we are mentioning. So now what will we see? If we run it, then we will see this Ia, variation of Ia with time, and variation of omega, speed. So what we are observing here, we can see when the speed is 0, that time this current is very high. That's why in our DC machine study, we always say we need a starter. We need a starter. Or the starting arrangement. Otherwise, the machine will damage. So this is the visualization. We can see that the starting current is very high, and as the speed builds up, this current will be very minimum, very low. So for this, what we are doing, we have several arrangement. And for the starter, we are actually adding some resistance with the armature circuit so that my starting current will be smaller, or we can use the reduced voltage starting by some controller. Now, let's say we are going for another situation. In fact, we can create a lot of scenarios. Now, let's say the machine was running fine. The same machine, it was running. Before it was in a stop condition, and we just started. Now we are going for another scenario. This scenario is the machine was running at certain speed. Now we want to stop it, or we want to break it. So this scenario is, let's say this is the machine parameter. It was running at 220 volt, and suddenly we change the input voltage to minus 220. This operation is called the plugging operation. That means for the electric vehicle, especially for the electric vehicle, if we want to stop it, then we need to reverse the voltage so that it will create the reverse torque and the speed will go down. Or, okay, so if you reverse it directly, then what will happen? So for that, we need to have an expression for the motor speed and also the time taken for the motor to reach the zero speed. So what will we do? We will do the same operation. That means, since here now the requirement is we have to find the expression of omega t. That means the mathematical equation. And that thing also we can solve it using this Matlab. Instead of the numerical solution, we will go for the another kind of solution. That means this is called the symbolic Matlab solution. So what will we do? We'll take the, first of all, we'll find the initial values when we are changing the switch. So before changing the switch, whatever the state was, that is my initial value. And then we'll solve this differential equation by taking the Laplace, then doing the partial fraction and the inverse Laplace. And in fact, we teach this thing in our this signal and system course. And for the part B, we will solve it numerically. So let us look at. So with the symbolic Matlab solution, we can find this expression for omega t. Instead of a number, we can find, create a expression. Or similarly, we can also get the expression of IA. And here is the variation of omega t with time. So we can find when it is reaching zero speed. So we can find this time from this graph and get the solution for time taken for the machine to reach the zero speed. So if we just leave the machine in a reverse polarity voltage, then what will happen? You can see the machine is reversing its rotational direction. Initially, it was close to 300 speed radian per second. Then it will reach to zero speed and then move to minus close to minus 300 in a reverse direction. But what will happen with the current inside the machine? This thing we did not see it. So you can see if we reverse it directly, then the current will reach very high, over 1000 ampere. So that will definitely damage the machine. So for that, what arrangement we have to do? We cannot reverse the voltage polarity directly. Rather, we have to change it gradually so that the difference between the internal voltage and the terminal voltage is remaining same, so that the current will remain in certain limit. So that thing, let us see in our Matlab. For this, 1 minute. Where is this? Okay. So the first part, I'm solving it using symbolic Matlab. And for symbolic Matlab, we have to just declare. Okay, 1 minute. Okay. we have to use this sims and declare what are the variables we want to consider as a symbol. Even the numbers also you can consider it as a symbol. So if you put it in this statement sims, then it will, whatever the variable you are mentioning, so that will be considered as a symbol. And here basically I am doing this Laplace, then partial fraction and inverse Laplace. So here is the inverse Laplace. And after this, we are getting the solution, this one, IA and omega, these two. So let us run it. And this is also very interesting sometimes. Okay. So this is the solution it is giving, whatever I showed you in the slide, exactly the same solution it is giving me. But look at, this is the expression. This is not in a certain value. So this one is, this variation is following this expression. Similarly, this one also following this expression. This variation also following this expression. Now, we can create many other scenarios. So let's say we, instead of reversing to full voltage, we reduce it to half of this rated voltage. Then how the current will vary and the speed will change. So this plugging operation. So here I am solving basically these two differential equations. So to see the variation is omega, and initially it was with the positive speed. Now it is the negative speed. And if we do not take care of the input voltage variation, and then the reverse current may rise very high value. So this is the information it is giving you, or this is the message it is giving you. Okay, now we will go for another, that is for the renewable energy sources. That is, nowadays the world is moving towards the renewable energy, and this is this diagram actually from one of my papers. So we frequently use the wind turbine for the wind generation system, and then with this wind turbine we attached with the induction generator for converting our mechanical power to electrical power. So here it is generating this mechanical power, whatever we do in our power station through the turbine. So here we are running this turbine using the wind. Now the characteristics of this wind turbine, this is a complex, it follows a complex equation. This is not a simple equation. So the mechanical power it is generating, let me put it, the mechanical power it is generating that is following this equation. So half this rho, this is the air density area, this is the area of the blade or the swept area we call it, and Cp, this is called the power coefficient. So this is not a what you call it the fixed value, but it has a complex expression for the Cp itself. And this delta, this is called the tip speed ratio, lambda. This tip speed ratio is this, and this beta, this is the pitch angle, and the omega, VW, this is the wind speed. So here the wind speed is the only variable. The other things, this is, we can say for a wind turbine, this is fixed. Now, also blade pitch angle also variable. So this is not constant. So we can control this for controlling this output power. So the thing is, now the Cp, it has the complex equations where this lambda I one is related to with the pitch angle with this equation. So now all this giving us a complex expression. So now how can we characterize this wind turbine for different values of wind speed? So if we can solve this set of equation, whatever I just showed you, this set of equation for a certain pitch angle and certain wind speed, then we can get a curve like this for wind speed like this, that is 9 meters per second. If we keep on increasing wind speed, then the variation will look like this. So this is a quite nonlinear variation, and where we have a peak value, this peak value here with this speed, wind speed. So the power is varying, reaching at peak value, then again going down. So again, this for this speed, that means wind speed. This VW is the wind speed. It is starting with the lower value, then reaching peak, and then again going down. So similar thing happening with all other wind speed. So now for the wind turbine operation, you know, all the time we want to look for the maximum one. So we want to run the machine at the peak value so that we can get the maximum power from this operation. So this is called the MPPT locus, the maximum power point locus. So if we keep our operation along this line, then for every wind speed we can get the maximum power. So now how to plot this, or how to characterize this thing? Okay, I'll show you this in Matlab. So this is the variation of the wind power with certain only one wind speed, and this is a turbine rotor speed. So there are two speeds, basically two speed here. One is the turbine speed and another is the generator rotor speed. So here is the gearbox. With the gearbox we are changing this speed. So that's why, so this one is representing our generator rotor speed after now multiplying it with the gearbox factor, and this is for the rotor speed before we multiply it. And this is the CP variation of CP with the tip speed ratio. Okay, now I will show you turbine characteristics. So here, since the complex equation containing this lambda I, so here we are solving this lambda I for different values of lambda, and then after this we are solving for the turbine power here, and then plotting it. Okay, so it is in one shot, it is giving me for all the let me see whether I am giving any pause. No. So if I give a pause, then it will show me for each speed, that is wind speed, it will show me this curve one by one. So since I did not give this pause, it is giving me in one shot all the variations. So now for the MPPT, so we are just adding the peak point and getting the MPPT locus. So now what we can do, we can write a function subprogram which will have two input variables. One is this wind speed and another is beta. So if we need to control this beta for controlling the wind power, so we can. Because we cannot change the wind speed, but by changing the blade pitch angle, we can vary this wind power. So if we want to run for constant power, then we have to use this blade pitch angle control. So in this way, we can do some work on a wind turbine. And the last one is for the solar. For the solar also, the input is the solar radiation, and from the sunlight, the energy is coming to the solar cell, and then from the solar cell, we are getting the current and voltage at the terminal, and also the power. So now, how the voltage, current, and the power is varying with the irradiation or the radiation. So here the schematic symbol of the solar cell. So it has two input. One is G, this is called the irradiation, and this is the temperature. So this output power of a solar cell is depending on these two variables. And the model, it will follow that. In fact, in the literature, you can see the several model. One is called that single diode model, another is two diode model. There are simplified version also. So here I am using the single diode model. And the characteristics equation for this is like this. And again, this one, this is not a simple equation. So because there are many things we cannot measure, like the shunt resistance, series resistance, we cannot measure this ideality factor N, this VT, that is this thing N, RS, the shunt resistor, this thing we cannot measure. So we have to estimate this thing from the manufacturer's data given. And after this, we have to have a model of the solar cell, and from there, by varying our the temperature and the irradiation, we can have the set of curves for different temperature. So this is called the IV characteristics. That means how the terminal voltage that means will be related with the current. And this is the PV, called the PV characteristics. And we can combine these two together. So again, we can see there is a peak point for certain temperature and certain irradiation. And after, before this, it has a lower value, and after this also lower value. So again, for the wind turbine, we can also operate our solar cell for certain temperature and irradiation for the maximum power. So this is also called MPPT tracking. And so using this set of equations, we can solve this. 1 minute. These equations, and let's say both, and we can generate these curves. Okay, so now only generating this curve is not the main objective. In fact, we need to develop a function subprogram which will have the input of irradiation and the temperature, and the output will be the power and the current. So that we can know that for certain value of temperature and irradiation, this much power will get from the solar cell. like this, we can use the other sources of energy like fuel cell. So I will not go for this today. I did not prepare that one today. So that is the end of today's presentation. So if you have any question, you can ask, or if you need any help regarding this Matlab, you can contact me anytime. That's all.
Thank you so much, sir, for giving such an informative session, and I really appreciate your report. Now we will move towards our question answer session. You can ask any questions related to today's topic to our honorable speaker.
Assalamu alaikum, sir.
Walaikum assalam.
Sir, I have one query, sir. For example, in Matlab, sir, actually how we can address the aging effect of PV cell. For example, we know we can plot the characteristics curve, and due to some aging effect, the current decreases. So if we have a model of PV cell, how actually we can using that equation, how actually we can introduce that there have some aging. That means how we can make the difference between the two cells. This is a healthy cell and another one is aging cell. Do you have any suggestion?
Actually, I don't have this kind of simulation or the modeling of this. So I cannot say anything.
No problem, sir. Another thing is that, do you have any idea about that? Is there have any simulation model or Simulink model that where we can just modify that model according to our need in Matlab?
Actually, for modification, in Matlab, in the Simulink, you can see there are some built-in tools or built-in, we can say, models. But the problem with the built-in is you cannot change anything. So that's why we have to go for the basic equation, because with the Simulink model, or what they are solving actually inside the model, the input it is taking this G and T, irradiation and the temperature, and the output it is giving you this, we can say this is the current, voltage, and the power. But inside the box, what it is doing, this is it seems a black box to us, so we cannot change it. But now, if you, as a researcher, if you want to change it, if you want to modify it, of course, you have to go for the basic equation and build your own these function subprograms or own program, so that you can play with the numbers, you can play with the other variables also.
Okay, thank you, sir. Actually, I have seen almost maximum part of your presentation, and I found that very informative. And basically, for the students who actually want to start with Matlabs, definitely this lecture or this workshop will be beneficial for them. Thank you very much, sir.
Thank you. Thank you. Actually, this workshop or this webinar is targeted for the students and not for the experts. This is not for the basic or not for the very advanced. This is, we can say, intermediate level.
I think, sir, if the beginner starts from your slides, definitely tomorrow they will be an expert.
Hopefully. Any other question or any other query?
I think there is no more questions, sir. Thank you very much, sir.
Okay.
We are now at the end of today's webinar. Thank you very much for being with us. We will have another session of our series webinar tomorrow at 2 p.m. about compact antenna in wireless communication. Hope to meet at our second session. Till then, stay safe. Allah Hafiz.
Thank you very much.